now?
Yes, you can share the screen.
This one.
Yes.
Yeah.
So yeah, today we have Giancarlo Mattia, who just finished his PhD and moved to Firenze, and he will be talking about jets from accretion disks. So the floor is yours.
Hi. Well, thank you very much for attending this online talk. I'm Giancarlo. I did my PhD in Heidelberg, and this talk is mainly wraps up what I did during my PhD, and now I'm a postdoc in Florence, like I started roughly 2 months ago. Since, from what I understood, this is a quite informal talk, feel free to ask any question at any time of the talk. There's absolutely no problem. So let's start. The astrophysical context is astrophysical jets, which are very interesting objects in our universe. One of the primary features of astrophysical jets is that they span orders of magnitude in terms of extension, time, energy scale. So they can be quite ubiquitous. We can see them in the context of protostellar objects as well. It's AGN, which, as you know, like it's very different scales. So far, theoretical and observational investigations found that there are mainly 3 ingredients responsible for the launching of a jet. The first is an accreting object, then we need an accretion disk, and last but not least, we need a magnetic field whose strength and topology must be favorable for the launching process. Through the decades, many researchers, many astronomers investigated the relation between the disk and the jet, and most of the simulations already prescribe a strong order magnetic field. But the question that it's still unanswered is how does the magnetic field, which is responsible for the launching, originate? And this was the primary goal of my PhD, to start to tackle this question, to give a small contribution to the answer. There are some possible processes that can be responsible for the amplification of the magnetic field. For example, in case of a central stellar object, we can deal with a central magnetic field, or we can assume that the interstellar medium already has some magnetic field that then, after some MAT processes and astrophysical processes, gets to the favorable strength and topology. But what I focused on is dynamo, because it seems a very general process that can occur in both protostellar disks and AGN disks. And the investigating dynamo processes in accretion disks raises a question like, do we want to simulate the origin of the dynamo, so the turbulence, in a consistent way, or we want to focus on the large scale? One approach is to do what they are called direct dynamo simulations. So the turbulence that generates the dynamo is simulated directly, but in this scenario, we cannot really go to the large scales of the jet. And so we can actually have an amplification of the magnetic field, but then we cannot really investigate the properties of the jet. Another approach, which is the one I follow, is the mean field dynamo. So we don't really see the turbulence. We just want to mimic their effects on the large scale. In this way, we can investigate both the disk and the jet in a maybe slightly less consistent way, but without spending the age of the universe in computational time. The dynamo process has been studied, especially in recent decades, in order to understand the magnetic field in astrophysical objects. For example, Duda et al. Investigated a stellar dynamo, and one of the major parts where dynamo investigated is in accretion disks, both thin and thick, and also recently Coriolis et al. Investigated also the launching of a jet from a mean field dynamo accretion disk, observing from simulation covers a Blanford jet and also a strong weighted disk. In the simulations that I performed, I did 2D, and I focused on an alpha square omega dynamo. What does it mean? That we have both the dynamo and the rotation of the disk as amplification process for the magnetic field. In particular, let's start, for example, with a toroidal magnetic field. Then the dynamo effect will amplify a poloidal magnetic field. Now we have a poloidal magnetic field, and the rotation of the disk and the dynamo effect will amplify the toroidal magnetic field, and so on and so forth, until something happens that quenches, suppresses the dynamo. In turbulence simulation is usually a large scale magnetic field, but in mean field dynamo simulations, the thing is a little bit more tricky, and I will discuss a bit more in the next slide. But let's focus a bit on what is actually dynamo, because it seems a bit sketchy that we are just putting one additional term in the induction equation, and then we say, okay, now we replicate the turbulence in the accretion disk, and now we amplify the magnetic field. I mean, that seems a bit of a scam, you know. So a very important thing, a key point, is that we have to try to model the dynamo in the most consistent way, so we can actually have a direct link with the direct simulations and with the turbulence that we're trying to model. We know from previous investigation of analytical and numerical models that the dynamo tensor has some properties. For example, in principle is non-isotropic, so the components of the tensor are not the same at all. We know that if this disk is thin enough, we can neglect the non-diagonal components, because the non-diagonal components scale with the disk height. And this is what I did during the entire simulation. So I dealt with thin disks. There's also some additional properties, like there's a dependence on the midplane sound speed. We can safely assume that the dynamo changes sign across the midplane. And also a point that I started discussing 2 slides ago is that here we don't have the suppression of the MRI and the turbulence from the magnetic field. So we have to find a quenching strategy for the dynamo. We have to suppress the dynamo in some way. Otherwise, the magnetic field will increase exponentially until our simulation crashes, because we have very unphysical values of the magnetic field. So how can we reproduce a consistent dynamo? Which are the steps that can be done, and which are the questions that we can ask ourselves? So we can ask ourselves, what are the effects of non-scalar dynamo? So the dynamo is not actually a single value. It has different values for different components. How can we constrain them? Because more components means more degrees of freedom, and it's very hard to go toward a consistent model if we have more degrees of freedom, because then we have to parameterize them in some way. How can we suppress the dynamo in case of a large-scale magnetic field, which should suppress the turbulence? And also, the eta, the diffusivity, is also a turbulent process. So how can we link the dynamo and the diffusivity? Should we also suppress the diffusivity in presence of a large-scale magnetic field? So in order to tackle these questions, I performed numerical simulations of jet launch by a non-isotropic accretion disk dynamo. And that was the main thing that I did during my PhD. So I used the Pluto code, which is a great code. I'm very happy with that. And I implemented the dynamo in the resistive MHD module. I did 2D simulations, so I assumed axis symmetry, and as initial condition, I started with a thin disk surrounded by a hot core. For the magnetic field part, I started with a very weak seed field, so magnetization of 10 to minus 5, and I started with an initial radial field, just because it was very simple to implement, and in principle, the dynamo shouldn't be dependent on the initial condition. As first step, what I did was to study the effect of the different dynamo components, and we tested a toy model where we changed by hand the single components in order to understand which is the effect of the single components and disentangle their effect. As a second step, we applied a more consistent dynamo model where the dynamo and the diffusivity coefficients descend from mean field theory and are not just parameters that come from our creativity, let's say. And as a third step, I studied different feedback models in order to suppress the dynamo, and I tried to also link the dynamo and the diffusivity by suppressing the diffusivity as well. Now, since one of the requirements of this talk was to discuss some potential numerical issues, I put 2 slides about things that became a bit tricky during this work, and they are worth it to stress. First is the Riemann problem. Now, as Pluto is a finite volume scheme, so in order to compute the flux between the cells, we have to solve the Riemann problem. Now, there are plenty of Riemann solvers available. You have linear, like the rho, the non-linear, like the HLL. You have also other like Mustad, G-force, and so on and so forth. You can choose your own Riemann solver. But most of my simulations, I would say basically all my simulations, like 90% of them, I apply the HLL type Riemann solvers because they are stable. Most of them, they are quite accurate, and their integral representation allows us to start solving some slows that are not completely included into the scheme. So they have really nice properties, and also if we don't consider the HLD, they are also fairly easy to implement. But here comes the point. The dynamo equations have the induction equation now with the dynamo has an additional dynamo term, which changes the eigenstructure of the MHD equations. So to adopt the HLD would have required massive modifications to the Riemann solver, because if you then try to compute the eigenvalues of the MHD plus dynamo, you see that the alpha waves are strongly affected by dynamo. They have a strong dependence. The alpha actually is slow wave, while the contact wave and the fast waves are basically unchanged. So we started with an HLL solver because it's the most robust that we have. Although it's pretty diffusive, but it's the easy, it was the easy choice in the beginning. Then we moved to the HLLC solver, which is more accurate because it allows us to solve the contact wave, and also it didn't force us to do modifications to the Riemann solver structure. Nevertheless, sometimes the Riemann solver is less robust than the HLL, especially when there's a strong magnetic field or when the magnetic field is rapidly changing. So in case of numerical issues, we switch to the HLL Riemann solver, which ensures more stability of the code. Another issue are the boundary conditions. And I'm pretty sure that every numerical person knows that this is probably the most painful part of simulations, because you really never know what to put in the boundary conditions. So this is the thing that is worth stressing. In particular, the condition, the inner boundary conditions, because we have the disk in our domain. And since we're not dealing with general relativity, where we can use Kirchhoff coordinates where the inner boundary can penetrate the event horizon, we have to model the inner layer of the disk in the boundary conditions in a consistent way, let's say. So for the hydrodynamic quantities, we assumed a power law for pressure and density in both disk and corona, and we assume that no matter can come from the central object to the disk. For the magnetic field, we dealt with the...
Sorry, seems like Ilek has a question.
Oh, yeah, I cannot see if people have raised hands, so just please unmute your microphone. I mean,
okay.
Yes.
Thank you, Giancarlo. Sorry for interrupting, but so I was wondering here at your inner boundary, you have to be careful about the boundary conditions because you are not inside the event horizon. Your inner boundary is right on the event horizon. You are not using Kirchhoff coordinates.
No, I'm not. This is non-relativistic. That's why.
Sorry. Okay.
Yeah, that's why. Well, there was an example, especially because we had like last week Oliver's talk. So and they use Kirchhoff like quite a lot. So these are non-relativistic. So we cannot do that amazing thing that are the Kirchhoff coordinates. So we have to deal with the inner boundary of the disk, and that's probably the most painful part of the boundary process here. And so
okay, cool, thank you.
The other, yeah, thank you. It was a really nice question. So the hydrodynamic quantities was dealt in the way that I described before, and for the magnetic field, we actually tested different options. For the first simulations, we just assumed a fixed slope of the magnetic field at the inner boundary, as you see from this image. This is just qualitative, but you get the gist. And for the simulations where we tested the feedback here in the coronal region, we just ensure the conservation of the magnetic flux. These are probably not the best boundary conditions ever, but first of all, they shouldn't really play a big role. in the launching process. And second of all, it's really a tricky game of having stable simulations where the boundary doesn't really play a role, and the most consistent simulations. Because if we start, for example, putting magnetic flux from the disk to the coronal region, just because we let the magnetic flux flow, then the code can crash at any time. And so this is, although we expect the magnetic flux to be active in the inner regions, that can lead to numerical issues that the code is can struggle to handle. So we also have to compromise in this sense.
Yes,
So,
Giancarlo, sorry.
Yeah.
And what do you do for the density, for example?
The density, we just
boundary?
assume the power law. It's quite stable and also, I would say, fairly consistent, because we assume that both the disk and corona follow a power law in the radial direction. So we just assume that the power law is also preserved in both shots.
Okay, so basically the power law at the power law at a given time, or the power law at t equals 0?
No, we assume we adopt the power law at t equals 0, but we also see that the dynamics of the disk doesn't really change that much. So we have also tested the radial dependence. We also did like some fits in order to understand if the power law had changed. And for the density, for example, changes from minus 1.5 to minus 1.35. So it doesn't really change that much, so that we require changes in that. Overall, the structure of the disk it's fairly unchanged unless something very strong happens, and I will talk a bit really quickly in one slide. But it's very rare that the disk structure changes so much. So we can assume that in the inner region, the density stays roughly with that power law. So back to physics. So let's run our simulations and let's try to answer some of these questions. So why do we need a non-isotropic dynamo? Cannot we just use a scalar? It's fairly easy. It's easier to implement. It's easier to parameterize. So why do we need something like that? Well, here there are some simulations where I changed the parameters. So here in the second from the left, I changed the phi component. In the third from the left, I changed the r component. And in the last race simulation, I changed the theta component of the dynamo. And as you can see, that there's some difference compared with the scalar. So they are all slightly more, let's say, turbulent. And here you can see that there's an anti-aligned magnetic loop in the disk. And what is happening here, I mean, it seems pretty different from these nice simulations where there's this loop here and then gets affected, pushed away, diffused away, and then these lines that are very compatible with the Blanford plane. So what's going on here? I mean, the dynamo components really play a role because you can just see it visually. The outcome is different. So if we change the components, we actually have a different outcome. And which is that outcome? So since we are 2D, the phi component is the only one responsible for the amplification of the colloidal field, which is responsible for example, the Blanford plane outcome. So we expect that a stronger phi component leads to a stronger amplification of the magnetic field, which is exactly what we get. And here there's the magnetic energy at certain radius. And you can see that if we multiply the phi component by 0.1, we get very low amplification, while if we multiply it by 2, so 20 times larger than the blue line, we also get a stronger amplification. And one very important interrelation that was recovered in non-dynamo simulations of jet launching is the relation between the disk magnetization and the jet speed. And in these dynamo simulations, we also retrieve it, but this time as a function of the phi component of the dynamo, because it's the responsible one for the amplification of the magnetic field. So stronger phi component, stronger magnetic field, stronger disk magnetization, faster jet. So we retrieve the same relation that was performed in resistive simulation, non-dynamo simulation, but this time without assuming a strong magnetic field from the very beginning. We start with a low magnetic field, the magnetic field is amplified by the dynamo, and this plot is retrieved very naturally. So we can say, okay, perfect. I mean, we have the phi component. What else we need? No, because the other components also play a role, and most likely in the topology of the magnetic field. So by playing with the R component, we see that when it's strongly non-isotropic, some anti-aligned field magnetic loops are formed in the accretion disk. These magnetic loops form, and in the layer between the two aligned, the anti-aligned magnetic field lines, the magnetic field is not amplified. This is we call them dynamo inefficient zones. You can see one here in the low right plot. Here is plotted the magnetization of the scalar model on top, and on a model where the R component of the dynamo is strongly and non-isotropic. And you see that there's a part of the domain where the magnetic field is not amplified. The magnetization is still low. In these zones, in the disk that then propagates also in the corona region, the magnetic field cannot be amplified. The dynamo is not efficient, and that's why we call them dynamo inefficient zones. If they are far enough from the domain, from the inner domain, so from the, let's say, the central object, they don't really play a role. But when they are very close to the central object, they can affect the evolution of the disk quite strongly, because there's no diffusivity in that region, because we assume that the diffusivity depends on the magnetization. And so there are parts where the matter cannot really have a strong inflow from two really close region of the disk. So there can be breakpoints of the disk that strongly affect the accretion and the ejection process. And what does the theta component does then? Well, the theta component plays a similar role to the radial components. But when we start with a radial magnetic field, the theta component doesn't play a role until you really boost it. Like in this theta A simulation, I put a factor of 5 in front of that. Because once the magnetic field is amplified enough to get the theta component of the dynamo to play a role, then the magnetic field is already saturated, because we started with a radial magnetic field. It depends on the initial condition. And when we boost it, so it starts playing a role from the very beginning because it's much stronger than the others, multiple inefficient zones are formed. And we find that the efficient zones tend to reconnect with the closest one. So this is with this one, and then there's this one that closes with the other one, and this has to close very far because it just gets like lonely. And these two connect to each other because they are the closest. And this happens in case of an initial radial magnetic field. In case of an initial vertical magnetic field, for example, we get a similar picture. But we can encounter some numerical issues. And this is because the theta component of the dynamo is strongly non-isotropic. And it's highly overestimated in presence of a scalar dynamo. So how can we constrain the dynamo components now? We played a bit with the parameters, we saw there were some differences, but now we want to be more consistent. So what we did was to apply the standard dynamo model of Rudiger, 1995, where the three components of dynamo and diffusivity are directly linked with one single parameter, the Coriolis number. Let's say, practical definition of Coriolis number is the effect of rotation on the turbulence. And practically speaking, it means that the high value of the Coriolis number means a strong dynamo, and a low value of the Coriolis number means a weak dynamo, which reflects on the amplification of the magnetic field, of course. So let's now apply this model, and let's see, can we actually get a jet launched from the accretion disk? So we see from the right plot where I plot the magnetic energy that the magnetic energy is strongly amplified in the inner region of the disk by the dynamo. And the magnetic field line starts to open up and get lifted up with the matter that is ejected. In the beginning of our simulation, we have magnetic loops rooted at different places of the accretion disk, and this is a clear indicator of a tower jet launching mechanism. But as the time goes, the magnetic field lines let's say it changed the orientation to more standard blindfold pay outflow mechanism, especially when they open up because we reach the end of the domain. As the simulation goes, the magnetic field is diffused, and also the dynamo starts to playing a role also in the outer regions of the disk. And we can see that at radius 50, it needs a bit of time for the magnetic field to amplificate, but it still goes and it increased by a couple of order of magnitudes. And arrived at time 1000, the inner region basically reaches a quasi-steady state. So that's why I stopped. They can run longer, but there was no point in showing you a video where basically everything is the same. So we see that we get a jet, but the tricky point of the Coriolis number is that there's no one single value that can reproduce all the jets, because the Coriolis number can be retrieved from turbulence simulation, but there's still some distance between direct simulations and mean field simulations in this regard. So best thing to do for us was to perform a parameter study of the Coriolis number and see how these values changes the disk and jet structure. So if we have a fairly high value, like 10, which is where the Coriolis number cannot get much, the dynamo cannot get much higher than that. We see very nice open magnetic field lines. This is the toroidal field, and it's fairly continuous. There's no sharp breaks in the field. We have a very strong amplification of the magnetic energy, and this seems pretty fine. If we decrease the value, for example, to 1, we see that the R and theta components start playing a stronger role. So we have anti-aligned loops and formation of dynamo inefficient zones. And you can also see it here in the toroidal magnetic field, because as I mentioned before, the magnetic field cannot really be amplified in these zones. And also because the phi component is lower, the magnetic field is amplified to lower magnetic energies. If we decrease it even more, we have this messy turbulence structure, which does not correspond anymore to a strong collimated outflow. It's more like a slow uncollimated wind. And as you can see, the magnetic field is not strong enough to be carried away so much. So a stronger dynamo effect leads to a stronger magnetic field amplification with all the consequences that are carried with this statement. So also faster jet, more collimated jet, so on and so forth. Now, the feedback of the magnetic field. I said before, large magnetic field kills the turbulence, but we don't have the turbulence, we just mean their effects. So how can we actually suppress the magnetic field? We tested several, well, now we're showing through, we tested several models because there's actually no consensus on which is the best representation of the feedback model. So we started with the diffusive quenching that was developed by Stepanov a couple of years ago at MPA also, and the base of this, the concept of this feedback model is that the dynamo is not suppressed, but the diffusivity is boosted up so that it counterbalances the dynamo. Then we tested fairly standard quenching, who has a scalar profile, so it doesn't depend on the dynamo component, and it has a dependence on the magnetization. Magnetization to the power of -1. And then we also tested a non-isotropic feedback model, also developed by Rudiger and Cuscitino, because if the dynamo is not a scalar quantity, then why should the feedback be in scalar quantities? I mean, it makes perfect sense to test something that is non-scalar. The quenching, in principle, can have a strong impact on the saturation of the magnetic field and dismagnetization, and also, since it may play with the isotropy of the dynamo, can also play with the topology of the magnetic field. So a question that we ask ourselves is, are the jet properties affected? Like the relation between the dismagnetization and the jet speed that I showed before, it's still retrieved. So these are the simulations that I showed before. So we see some kind of qualitative relation between the dismagnetization and the jet speed, and we see low Coriolis number, low amplification, small magnification of the magnetic energy. So now let's see the other mechanisms. The standard model, standard quenching, reaches lower magnetic energies. Why that? Well, because the diffusive quenching, as I said before, doesn't really suppress the dynamo. It just boosts up another mechanism that balances it. So the amplification of the magnetic field is still there. It's just balanced by another physical process. While here, the dynamo is actually really suppressed. And that's why we reach lower energies. And when we put also the non-isotropic feedback model, we see that it reaches even low saturation values of the magnetic energy. And that is because the dependence of the dynamo, the magnetization on the dynamo, it's stronger. And so the magnetic field is saturated at lower values of the magnetization. Nevertheless, we see that there's although quite qualitative, but there's still quite good relation between the dismagnetization and the jet speed. So we can safely assume that the jet properties do not really depend when on the feedback method when we apply it only to the dynamo. But now what happens if we apply it also to the diffusivity? Because the diffusivity is also...
Giancarlo, sorry,
yes.
At the previous slide, so each point, it corresponds to like one snapshot in the simulation?
Okay, so we took the magnetic field lines at from times 700, which is basically good time, so the jet has already reached the outer domain. And so we tried and we linked the dismagnetization at the bottom of the magnetic field line to the jet speed at the outer boundary. And we did that from time 7 to time to time 700, from time 700 to time 10,000, which is where we stop, because if nothing happened at times 10,000, it's very likely it will not happen after. So there are these are at different radii and at different time, but we these are quite indicative of the portions of the jet through time. So if we want to see, for example, lines at the same time, yes, it's possible to do that, but we prefer to check if this relation doesn't only happen at the specific time, but at every time and at every part of the jet. Because we used, for example, 2 or 3 lines to describe this jet relation at the same time. It could be refined, but it already gives the, let's say, the trend of what we get. Of course, different portions of the plot are populated with different lines, because, for example, the diffusive quenching, the one in the screen, reaches higher value of the magnetization because it reaches higher value of the magnetic energy. And so we expect it to populate more the right part of this plot, while the other feedback models populate more the left part. This is something that we saw also when we applied only the diffusive feedback model, but with larger range of values of the Coriolis number from 0.1 to 10, and you reach roughly the same relation. Yeah. Okay, so let's try also to suppress the diffusivity. So we applied more consistent model of the diffusivity, which includes the suppression caused by a large-scale magnetic field. So now we have non-isotropic dynamo feedback, non-isotropic diffusivities. Everything should be the most consistent possible. So let's see what we get if we actually see something that is worth doing all this level of complexity. So this is the simulation with the non-isotropic dynamo quenching, which we also adopted in our more consistent model. And when we overlap it with our consistent model, we see that there are small differences in the magnetic energy, especially when the Coriolis number is high, but we see strong differences in the disk jet connection. This happens because the jet is collimated very early, and the magnetic field saturates, the magnetic field amplification goes a bit less in the jet speed as process and more in the collimation. We are still investigating if this is a problem of the initial conditions because we started the radial magnetic field, or if this is actually a physical thing. But the magnetic energy stays, say, very similar values, but here it's much more messy. If we have low Coriolis number, it's much more messy. So why that happens? It happens because there are some strong deviation from the steady state. So it's very nice when we do launching simulations and we reach a quasi-steady state, and that's very nice and everyone likes it. But we also, as a let's say first order approximation, also second order approximation, is still fine. But we also know that in jets, there are shocks, reconnection, there's turbulence, there are messy structure. The jets are not just uniform tubes that are lifted up, but everything that deviates from the steady state, it's worth like trying to see what happens. So what happens in this simulation is that because of the feedback on dynamo and diffusivity, some magnetic lines are lifted up and they tend to reconnect and change their topology because of dynamo. So what happens is that once they are lifted up to the disk region and they reconnect, they lose energy and lose processes that counteract the gravity. So now they don't really have nothing that stops gravity from pulling them on the up to the central object. So what happens is that they reach the base of the jet, and they basically break it because they enter into the inner region at the base, at the top of the disk region. So now, since they have different polarity, what happens is that the quenching is suppressed, the dynamo is restored, the magnetic field is re-amplified, and a very strong jet is launched. Then the quenching is restored again, and we get a configuration before this. We call it flare, but it's this quasi-periodic ejection. Now, let's see this video. I took some time because everything happens really quick. So you see on the left plus that there's something that is going, it's getting slowly accreted. It reaches the base of the jet, it shuts the jet, the magnetic field is amplified, and then there's this strong jet coming from very inner region of the disk. This is very fast and also very turbulent. And now the magnetic field goes back as the quenching is restored. And you can now see, like, let's see it a second time, that at the end of this video and the beginning of the video are quite similar. We detected 4 of these events, and every time they start at a different location and an outer location of the accretion disk. So the reason why we detect only 4 of them is basically because we assume a finite accretion disk, and we assume a finite accretion disk because we cannot really evolve the accretion disk outside our domain. So in conclusion, the dynamo and the diffusivity are definitely not scalar, and the relation between the components really play a role in this jet connection. Different forms of the dynamo strongly affect the disk and the jet properties, and it's possible to model the dynamo and the diffusivity following analytical mean field and turbulent theory. And this is actually a very promising process to explain the features that we see in jet, especially the large scale magnetic field. Thank you.